So our second speaker for today is Marina, who will be telling us about isospectrality and effective field theory extensions of general relativity.
Okay, so first I'd like to thank the organizers for giving me an opportunity to talk today. So I'm going to talk about a paper I put out back in July with Pablo Cano from the University of Barcelona. So I don't need too much of an introduction for this audience, but a little bit is not a bad thing. So just like particle physics has its own successful standard model, gravity has its own successful version of the standard model, which is general relativity. And so there's impressive experimental evidence, just like particle physics. And the most exciting one in the past 10 years or so has been the study of gravitational waves. Okay, but GR is not perfect, just like most theories. And now we know that GR must be seen from the lens of effective field theory, and that GR is just a low energy theory from a higher energy theory of quantum gravity. And so what you need to do then is you need to consider a Lagrangian. This is very schematic, and you need to include higher order corrections that account for looking at higher energy scales. So again, this is schematic. So alpha here is just some coupling, and then the curly r squared just means curvature variance of quadratic order, of cubic order, and so on, depending again on how your energy scale. So there's two ways to really look to study effective field theories, right? So you can do this from a top-down approach, where, for example, you take string theory, you can dimensionally reduce, and then maybe study it via T-duality, S-duality, and so on. Or you can take a bottom-up approach, which means that you come up with an effective field theory, not a crazy one, but just something that sounds reasonable. And then you impose, various physical constraints. So, for example, unitarity, causality, and so on. And so today, I'm going to talk about the second approach, which, the bottom-up approach. And I'm going to present to you a new class of effective field theories. And the overall idea of these new AFTs is that there are certain properties of general relativity that are typically broken when you go beyond GR. But in this case, we want a class of effective field theories that preserve these properties. Okay, so in order for me to discuss or tell you what these properties are, there's going to be two of them. I will have to tell you a little bit about gravitational wave propagation. So gravitational waves, this is very a known prediction, that gravitational waves propagate along null geodesics. And what you do is you can get the linearized equation, then from that you can compute the dispersion relation, and you find that it equals 0, therefore null. However, in beyond GR physics, gravitational waves are not null, nor are they geodesic. And the reason why that is because now this right-hand side is no longer 0. In fact, it will depend on the higher order couplings, curvature invariance, and so on. And then you may also run into birefringence. So the idea is you can kind of think of it from optical physics. So you have a pencil and you have some crystal on top of the pencil, and you have two polarizations, so you end up getting this double image. And so gravitational waves in beyond GR will also depend on the polarization, and so you'll get birefringence. Okay. So the second theme of these properties I want to discuss has to do with quasi-normal modes. So very generally, if I have an in spiral, eventually they're going to merge, and then the ring down is when you just have one black hole again. And so in this region, which I highlighted in yellow, is the ring down, and you can see that you have some decaying modes here, and these are the ones that are called quasi-normal modes. So these are the characteristic frequencies that people study. So what happens? So in GR, in vanilla GR, you compute your black hole perturbation spectral theory, and you find two sets of quasi-normal modes, so two families. And they're typically called axial and polar. And then you go ahead and you compute your quasi-normal modes, and you find an identical spectrum. And this is the property of isospectrality. So the quasi-normal modes are isospectral. So beyond GR, oh sorry, not yet. So just to give an idea of what this means, I just wanted to plot the real part of the quasi-normal mode frequency. So on the bottom axis here is just chi, which is the spin parameter. So chi equals 0 means no spin, so Schwarzschild. And then as you approach 1, you're getting an extremal black hole. And so then I'm plotting both axial and polar, and as you can see, there's only one line because the axial and polar are on top of each other because they're identical. And now in comes GR plus corrections. This is no longer true, so you do not have isospectrality. It is broken. And so as you can see, I have a blue line here and a red line here. They do, have some coincident value at like 0.25 or 3. But okay, in general, they're not going to be equal. So given these two properties, I can ask the question, is there any extension of general relativity that preserves both of these properties, isospectrality and non-birefringence? So the quasi-normal mode families are equal, and the dispersion relation is polarization independent. Okay, so obviously the answer is yes, otherwise I wouldn't be giving a talk. And so in case you're very excited, I'm just going to give you the results now and then hash into the details momentarily. So yes, we found a new class of theories. The dispersion relation is non-birefringent. And moreover, if you compute the quasi-normal modes in the econo limits, so your L, M, and N are the quantum numbers, and if you take L to infinity, this is the econo limit. And the quasi-normal modes in this case are isospectral. So two caveats or two remarks I want to make. If you don't take L to infinity, you do not have isospectral theory. So this is kind of a property when you take the large L limit. And then 1 really implies 2, because when you compute the dispersion relation, you assume large angular momentum, which is like taking L to infinity. So really 1 implies 2. Okay, and so from now on, when I say isospectral EFTs, I just mean that I have an effective field theory that satisfies both 1 and 2. Okay, so just to give a quick intuition about econo quasi-normal modes, there's a correspondence that says that unstable photons here in geodesics are related to these econo quasi-normal modes. So if you have a quasi-normal mode frequency, you have the real part plus the imaginary part. The real part is related to the orbital frequency, so how many times this goes around. And you also have the Lyapunov exponent, which is the imaginary part of the frequency, which is why, as you can see here, eventually the photon leaves this orbital motion. And so beyond GR, you could also expect a similar correspondence, right? So in this case, they're not geodesics, but there's some gravitational wave orbits that are going to be dual to some quasi-normal modes. And likewise, if you have some orbits that are non-birefringence, then you have isospectrality, and these quasi-normal modes are isospectral. Okay, so it's all related. Okay, so now I'll go to the actual EFT. So I want to write down an effective field theory. I want to write it down up to quartic order. Moreover, I want to have parity preserving and parity violating terms. So I have the Ricci scalar. I should have also an L4, but upon field redefinitions, you end up finding that it's topological, so that's why it doesn't appear here. And then you have your cubic terms and your quartic terms. And L is just some energy scale. Okay, so given these requirements, you get 5 terms, which is not too bad. So you get, so the explicit invariant of I and curly C is not too relevant, but I wrote them here on the bottom in case you're interested. So there's 5 terms, and then lambda and epsilon are just the coupling constants. And then the I tilde and then the CC tilde are the odd, or the parity violating terms, and then the rest are parity even. Okay, so you can ask the same question as I've been asking before. Are there any isospectral effective field theories? Given that we're starting from this theory. The answer is yes, and it requires certain properties of the EFT. So the first thing is you do not have any parity violating terms, which means you have to cross out this one and this one. It also means you cannot have any cubic order terms, so you cancel this one and then this one's already canceled. And then when you look at what's left over, you just have two terms, right? And you find that it has to be that the two coupling constants are equal. So essentially it boils down to just two terms and one coupling constant. Okay, so putting it out and writing it out explicitly, you have a term that looks like Riemann squared squared, and then Riemann tilde squared. So Riemann tilde here is the Riemann dual. And then you have one coupling constant. Okay, so as I said, there are three properties. No cubic corrections, parity must be preserved, and a single quartic correction. Okay, and then the last thing I want to say is that if you have your string, if you have a string theory, type 2 string theory in 10 dimensions, and you dimension reduce that down to 4, you're end up going to getting these two terms. So exactly the same theory that I found from isospectrality, you'll find it from type 2 string theory. Given, of course, that the coupling constant is proportional to alpha prime cubed, which is the first correction in string theory. Okay, so you can ask why this happens. So we're not totally sure, but we have some maybe guesses or intuition of why that is the case. You could say that it is related to supersymmetry. You could say that it's related to some duality, so maybe some hidden, either a hidden duality or maybe it's related to S or T duality, and it's being exhibited in a different way. And then you could also say maybe it's like a Born infield like gravity. Because in Born infield theory, when you do your expansion for small f, you get f squared plus f tilde squared. So it looks very similar, right? Okay, so just to conclude, so we did find a new class of isospectral EFTs. And so they have two properties. You have your non-birefringent dispersion relation, and you also have that the quasi-normal modes are the two families are equal, given that given that you're in the Econo limit. And then there may be a key feature of quantum gravity, although this is yet to be really investigated. Okay, so the last thing I'll say is just discuss the future directions, and we're currently working on these things. So the first thing you can ask is, are there any generalizations? Is this the only theory the only isospectral EFT? So you would have to then, for example, go to quintic order and so on, or maybe write an arbitrary Lagrangian made out of certain cubic and quartic invariants, and then study the independence of the polarization tensor coming from this theory. You could also study the phenomenology, right? So you can study the quasi-normal modes or some other aspects that could be interesting. And then finally, really understanding this connection to string theory, and from, whether it's some duality or something else that is yet to be uncovered. Okay, so thank you for your time.
Okay, we have time for questions. There's a question up there. And then there's supposed to be another one.
So what is the importance of the isospectrality property? Is it important experimentally? Is it important in other ways?
Well, I take an EFT and I want to study a property of this EFT, or I want to demand some property. I'm not saying that it necessarily has to, the world does not have to be isospectral, but it's an interesting thing, and there could be some connection to string theory, so, yeah.
Yes. When you have higher curvature corrections, so you mentioned this relationship between quasi-normal modes and the Lyapunov exponent. Is there a formula which is proven for
for like beyond GR, is there this correspondence?
Yeah, this
to be
dispersion relation relating the frequency of that.
So the correspondence is true for just GR, and I think it should be true when you add higher derivative corrections. I mean, the intuition is there, and the results roughly that I showed are supporting that.
So you're not using that, you're giving evidence for it?
Yeah, we're getting that, yeah.
Any other questions? We still have time, so
this connection which you mentioned with straight theory contact points, right? Is that a 4-dimensional thing, or is that true in two-dimensional contact points?
It's true in 4 dimensions because our EFT is in 4, which, I mean, it makes more sense to compute quasi-normal modes in 4 dimensions, especially from an homological point of view. Okay, but I haven't looked at other dimensions.
maybe I'll ask you a question. So I was curious because it seems, okay, correct me if I'm wrong, but it seems like you're imposing these conditions, thinking that these couplings are finite. Like instead of like, basically what I'm asking is like, would you have concluded something different if you truly had an infinite series of corrections versus just looking at like a truncated
this is
series?
Yeah, this is what I mean by generalization, right? I mean, maybe you can look at an arbitrary Lagrangian of arbitrary order and then impose isospectrality and see what you get.
Yeah, but if that order is like because there is a belief that you should have like an infinite tower of corrections and some small parameters. So I don't know if there's something that would change in terms of the analysis of like, am I imposing this like
will lead to infinite corrections or something like that.
Yeah.
It could. I mean, again, I feel like you would have to, look at it and kind of see what properties of the EFT that would require isospectrality. So it could be that there is a theory that requires an infinite sum, and then that would be very interesting too.
Thank you. Any other questions? In the audience? No? So let's thank Marina, I guess.